lecture basically is based on ethers and epoxide. This is a new class of organic compounds which we have not discussed so far. In this class of organic compounds, there is an oxygen along with the alkyl groups in the molecules. In the present episode of ethers and epoxide, we will emphasize only upon ethers, and in ethers we are going to discuss, we will first introduce what actually are ethers, then we will discuss the structure of ethers, the classification of ethers, we will also discuss the isomerism shown by ether molecules, then we will discuss the methods of preparation of ethers. Now, the introduction of ethers. Ethers actually are oxygen containing organic compounds that are considered as the derivative of alcohol. You can see here that in this here we have mentioned ROH, that is the general formula for alcohol. If we replace one of the hydrogen from alcohol, the resultant molecule formed is ROR, and this is nothing but the general formula for ethers. Ethers can also be considered as dialkyl or diaryl derivatives of water molecule. See here, this is water molecule having two hydrogen atoms. If we replace both the hydrogen by alkyl group, we get dialkyl ether. If we replace both the hydrogens by aryl group, the resulting ether is diaryl ether. Then ethers can also be regarded as anhydride of alcohol. Anhydride means removal of a water molecule from the starting material. Here the starting material is alcohol. If we remove a molecule of water from this alcohol, the resultant product is ether, and that is why ethers are also considered as the anhydride of alcohols. In this slide you can see we have shown the ball and stick model of ethers. This molecule basically is representing diethyl ether, the red ball representing oxygen atom, the black ball representing carbon atoms, and the white ball representing the hydrogen atoms. This ball and stick model represents anisole or methyl phenyl ether, and this, the third model, represents tetrahydrofuran, a cyclic ether. We will now discuss the structure and bonding present in ether. If you will look at the general formula of ether, ROR, you can see that there is no unsaturation seen in the molecule, and whenever there is no unsaturation, that means that the molecule has sp3 hybridization, totally saturated molecule, and that is why the oxygen atom in alcohol, ethers and epoxide is sp3 hybridized, and alcohols and ethers have bent shape which is like that present in water. The bond angle around oxygen atom in alcohol and ether is similar to, or should be similar to, the tetrahedral bond angle of 109.5, but it has been found that there is some deviation in this bond angle. You can see here that this is the molecule of methanol, the COH bond angle here is 109.5, and this is dimethyl ether, the COC bond angle is 111 here, showing that there is deviation in the normal tetrahedral angle. Now the question arises why. We will discuss this question in the next slide. We will now discuss the structure of ethers with respect to the hybridization in individual carbon and oxygen atoms. Here you can see that the general formula in case of ether will have COC bond angle. All the three atoms, both carbon and one oxygen, all the three atoms are sp3 hybridized. Here in the structure of ether you can see that oxygen is attached to two carbons, but oxygen here is left with two more sp3 hybrid orbitals having lone pair of electron, and actually the presence of this lone pair of electron in the sp3 hybrid orbital of oxygen is responsible for the repulsion between the orbitals, resulting in the bent structure or resulting in the distortion in normal tetrahedral angle. In ether molecule, we also see van der Waals strain. This van der Waals strain actually arises because of the size of the groups or atoms present in the molecule. We will see that in as we increase the size of alkyl group, there is more and more of distortion seen in ether molecule. In the next slide. In the present slide, you can see that we have 4 molecules written here. One is water molecule, the other one is an alcohol, and last 2 are ether molecules. Now, what happens when in case of water, you can see that there is distortion. The normal tetrahedral angle is 109.5, but here the angle is reduced to 105. The reason here is the repulsion due to the lone pair of electron present in the sp3 hybrid orbital of oxygen. The size of hydrogen also plays an important role. Size of hydrogen is small and repulsion due to lone pair is much more, which results in the decrease in bond angle along H, O and H. Now, when we go to an alcohol, you can see that methyl group is larger in size as compared to hydrogen, and because of which there will be some van der Waals interaction there, and that is why even though repulsion is there between these two because of this lone pair of electron, the bond angle goes quite close to the normal tetrahedral angle of 109.5. When you look at diethyl ether, you can see that the 2 ethyl groups are present along this oxygen. The 2 ethyl groups are much larger in size as compared to hydrogens, and when the size is large, then there is van der Waals repulsive interaction resulting in increase in bond angle to 111 degrees. The extreme example of distortion of normal tetrahedral angle is shown or is seen in diisopropyl ether. Here you can see that in diisopropyl ether, the 2 isopropyl groups are so large in size that they actually repel each other. As a result, the COC bond angle goes to a limit of 125 degrees. So, in case of ethers, deviation from normal tetrahedral angle is because of the size of alkyl group, and this deviation, this kind of distortion in bond angle is also responsible for the molecule to show some dipole moment. It has been found that oxygen atom here in ethers has slight dipole moment. As a result, diethyl ether has a dipole moment of 1.2 dBi units. We will now discuss the classification of ethers. Classification means how many different classes we can divide ethers into. Now, since we know that ethers are the molecule in which the 2 alkyl groups are attached to or attached together through oxygen, or the general formula for them is ROR. That is why the ethers are classified as symmetrical ethers or unsymmetrical ethers depending upon the nature of the 2 alkyl groups attached along the oxygen atom. If the 2 alkyl groups are similar, then we say the ether is symmetrical ether. When the 2 groups are different, like in this case, you can see that one alkyl group is methyl and the other alkyl group is ethyl. In this case, the ether is called unsymmetrical or mixed ether. Further classification of ethers is done as open chain structure or cyclic structure. Under the category of cyclic structure, we classify them as saturated ethers or unsaturated ethers, and then another class called aryl ethers. We have shown all these classes of ethers with the help of certain examples in this slide. You can see here, this is diethyl ether. This is an open chain ether as well as this is a symmetrical ether. This ether is methoxypropane. This is an open chain ether, but at the same time this is unsymmetrical ether. Here, this is tetrahydrofuran. This is a cyclic ether, and this diphenyl ether is an example of aryl ether. For giving names to ethers, the 2 alkyl groups present along the oxygen atoms are first named. They are placed in alphabetical order, and then after that ether is written. That is how we name an ether. Look, for this we will show this with the help of an example. Here in this particular molecule you can see that we have a methyl group, we have a secondary butyl group. Now alphabetically secondary butyl group will come first and then will come methyl group. So the name of the molecule will be secondary butyl methyl ether as has been shown here. In case of symmetrical ethers, the two alkyl groups are same, and that is why instead of repeating the two alkyl groups, like in case we will not say ethyl ethyl ether, on the contrary we will put prefix di in before the name of the alkyl group, and that is why the name is diethyl ether. With the help of some more example, we will discuss the nomenclature of ethers. In the first case, in this example you can see that one group is methyl group and the other group is tertiary butyl group. Again tertiary butyl is alphabetically preferred over methyl group, and that is why the name of the molecule, name of the ether is tertiary butyl methyl ether. Here in the second case, we have an ethyl group on one part or one side of oxygen and phenyl group on the other side. Ethyl comes before phenyl, that is why ethyl phenyl ether is the name of this molecule. We will now discuss the nomenclature of ethers according to IUPAC system of nomenclature. According to IUPAC system of nomenclature, ethers are named as alkoxy alkanes. Since we have two alkyl groups in ethers, one alkyl group is taken as alkoxy and the other alkyl group is taken as alkane. Out of the two alkyl group, the complicated or the alkyl group having more number of carbon atom is taken as the main chain or as alkane, whereas the substitution we take the alkyl group which has lesser number of carbon atoms. And then say for example, we have a methyl substitution, we want to convert it into the alkoxy group. So what we will do is we will simply replace YL from the alkyl group and add OXY to that, and that is why CH3O is named as methoxy, methyl removing YL from methyl and adding OXY. Similarly, CH3CH2O or C2H5O is named as ethoxy and this group as tertiary butyloxy. In this example, you can see that we have two alkyl groups which are similar. So whether we make this alkyl group as substitution on other or this alkyl group as substitution on other, it is not going to make much of a difference. The name of the molecule will be methoxymethane, showing that this one of the methyl group is substitution on the parent chain. In this case, the name given is ethoxypropane. You can see that the larger number of carbon atom are there on this side of alkyl chain, which is 3 carbon. That is why the main chain is taken as propane and 2 carbon alkoxy group, that is ethoxy is substitution on main chain propane. That is why the name given is ethoxypropane. Here in this case you can see that one side we have 3 carbon chain and on the other side 1 carbon chain. So 1 carbon chain will be substitution over the 3 carbon chain, but the methoxy group is substituted on position 2 of the propane. That is why the name given is 2-methoxypropane. Here in propane molecule at position 2, substitution of ethoxy group has taken place. That is why the name 2-ethoxypropane given to this molecule. A few more complicated examples here in which alkoxy groups are present along with some other functional group. Like for example, in this molecule you can see that we have 2-methoxy group attached to the phenyl ring. The name given to the molecule is para-dimethoxybenzene, that is at para position of the benzene ring we have 2-methoxy group. In this case, this is a cyclohexene, and since you know that the double bond if present in a cyclohexane ring gets preference over other substitution, we will number the molecule from this carbon atom which has the double bond, and that is why at position 4 of cyclohexene we have tertiary butyl substitution. The name of the molecule is 4-tertiary butyloxy or 4 tertiary butoxycyclohexene. We will now discuss nomenclature rules in case of ethers when both sides of alkyl groups are highly substituted, or in other words we can say for complicated ethers the nomenclature rules are a bit different. What we do here is that in this particular case you can see that this is the ether functional group present in the molecule. This side of the molecule has 4 carbon atom. With this methyl substitution, this part of the molecule also has 4 carbon atom, and substitution is on these two as well as on this carbon atom. So, when the molecule is so much substituted, it is difficult to name the molecule as alkoxy alkane, and then in this case what we do is that we consider the longest, or we see the longest possible carbon chain including oxygen of ether. That is, in this particular case you can see that a total of 8 carbon atoms or octane chain is formed in this molecule, with position 4 having oxygen atom. So, what we do is we will simply name the molecule as 4-oxa-octane, showing that in octane molecule at position 4 we have oxygen. Now, we have to give nomenclature to these molecules. Here you can see that this is a methyl group, these two are also methyl group. So, the name given to the molecule is 5-chloro-3,6,6-trimethyl 4-oxa-octane. Now, the question arises, why are we naming the molecule as 5-chloro-3,6,6-trimethyl 4-oxa-octane? Why not the other way? That is, why not we number the molecule from here so that the methyl and chloro substitution come at a lower number. But if you remember the rules of nomenclature, the minimum number is given to the functional group, and here in this molecule the functional group is the oxygen atom or ether linkage, and that is why the correct name for the molecule is 5-chloro-3,6,6-trimethyl 4-oxa-octane. Another example again emphasize the same issue. Here you can see that the main chain contains 7 carbon atoms and position 3 has a oxygen atom. Now, the name given for this molecule will be 5-bromo-4-chloro-3-oxaheptane and not the other way around, that is 3-bromo-4-chloro-5-oxaheptane. In the nomenclature of cyclic ethers, the cyclic ethers are actually considered as the heterocyclic molecules in which one of the atom is oxygen. Here you can see that in this particular example we have 4 membered ring having oxygen, and the name given to this molecule is oxacyclobutane. This molecule is a 6 membered heterocyclic ring having one of the atom as oxygen, and the name given to this molecule is oxacyclohexane. If more than one oxygen is present, then the name dioxa, and since the 2 oxygens are present at position 1 and 4, the name given to this molecule is 1,4-dioxacyclohexane, or simply this molecule is called 1,4-dioxane. These molecules are very good solvents for various reactions in the organic chemistry. Here we have the examples of ethers where more than one ether group is present. As for example, in this case this molecule is 1,2-dimethoxyethane. You can see that oxygen is present here as well as here. The IUPAC nomenclature of this molecule is 2,5-dioxahexane, and this molecule is a diether. Here in this molecule, this is a triether, and you can see that in a chain of 9, that is in nonane, we have oxygen at position 2, 5 and 8. So, the name given to this molecule is 2,5,8-trioxanonane. The common name for the molecule is diglyme, and this is a triether. This again, the 1,4-dioxane or 1,4-dioxacyclohexane is a cyclic diether. All these molecules are good solvents in organic reactions. We will now discuss the isomerism shown by ether molecules. Ether molecules if they have more than 4 carbon atoms, then they show two types of isomerism. One is functional isomerism and the other is metamerism. Functional isomerism means the isomerism in which the molecular formula of the compound is same, but they are represented by different functional groups. And metamerism is the isomerism in which the distribution of alkyl group along the functional group is different. We will discuss the two kind of isomerism with the help of example in the next slide. Ether molecule and alcohol are represented by similar general formula CnH2n plus 2O, and if we write the structures for the alcohols and ethers with molecular formula C4H10O, we find that we can write three structures, that is this 1, 2 and 3 for alcohols, and we can write three structures for ethers represented by formula 4, 5 and 6. If you look at compound 1 and 2 and 3, all of them are alcohols and all of them are functional isomers with compound 4, 5 and 6, because 1, 2, 3 are alcohols and 4, 5, 6 are ethers. So, 1 is the functional isomerism with 4 or 5 or 6, similarly 2 with 4, 5 or 6 and similarly 3 with 4, 5 or 6. But if you look at the structure of compound 4, 5 and 6, you will see that they differ only in the distribution of carbon along the oxygen. Here in this case, 3 carbons are on one side of oxygen and only 1 carbon is on other side. In this case, you can see both on both sides of oxygen we have 2 carbon each, and here again even though we have 3 carbon on this side, the substitution of this methoxy group is at position 2. So, the relation between 4, 5, 6, compound number 4, 5 and 6 is that they are metamers. We will now discuss the preparation of ethers. Ethers are prepared by 3 or 4 methods. First of all, we will discuss the dehydration of alcohol. The dehydration of alcohol can be achieved by the reaction of alcohol in presence of concentrated acid like sulfuric acid at high temperature. Here in this particular example, normal butanol reacting with sulfuric acid at about 130 degrees centigrade to produce dibutyl ether. This method of preparation of ether is restricted or limited to the synthesis of only symmetrical ethers. Why? The question arises, why the method is a good method for the preparation of symmetrical ethers, but if we want to prepare unsymmetrical ether by this method, it is not that good. The reason behind it is that if we start with 2 different alcohols ROH and R-OH, then the product formed will be 3 different types of ethers. We will get mixture formed and it will be difficult to separate the mixture of ethers, and that is why this dehydration of alcohol is a good method for the preparation of symmetrical ethers, but not for the preparation of unsymmetrical ethers. We will now discuss the mechanism of reaction or mechanism of dehydration of alcohol. If we start with a primary alcohol, the 3 steps in the mechanism are: first step is the protonation of alcohol. If acid, in presence of acid, alcohol gets protonated and forms protonated alcohol. In the second step, the alcohol molecule, which is a weak nucleophile, attacks the sp3 hybridized carbon and there is removal of water molecule, formation of protonated ether. This mechanism is which is followed in here in case of primary alcohol is SN2 mechanism or substitution nucleophilic bimolecular, in which there is no formation of carbocation, but the nucleophile attacks from one side and leaving group goes out from the other side. In the third step, removal of proton from protonated ether and formation of ether. So, this is how a primary alcohol is converted into ether by the dehydration method. The mechanism of reaction in case of secondary and tertiary ethers follows first step as the same as that we have discussed in case of primary alcohol, and that is the protonation of alcohol. In the second step, however, instead of attack of the weak nucleophile alcohol from one side and removal of water from the other side, first there is removal of water molecule from the protonated alcohol and formation of carbocation. This carbocation has planar geometry and gets attacked or gets reacted upon with another molecule of alcohol and generate the protonated ether. The mechanism followed here is SN1, that is substitution nucleophilic unimolecular. In the third step of this mechanism, again it is the same as we have discussed earlier, the removal of proton from the protonated ether and formation of the ether. It has been found that if we start with secondary and tertiary alcohol, the product is most of the time or almost always an elimination product and not the substitution product. And as you have seen, if we want to prepare ether, we require substitution product and not elimination. The question arises why? First of all, we will see what happens here. We are starting here with isopropanol. When it is treated with sulfuric acid, there is formation of propene along with this diisopropyl ether. The diisopropyl ether is produced from isopropanol by substitution reaction, whereas propene is produced by the elimination reaction. And as shown here, you can see that elimination product is the major product. So, in other words, we can say that if we want to prepare ether from a primary alcohol, then dehydration of alcohol is a good method. But if we want to prepare a ether from secondary or tertiary alcohol, then that is not a very good method because yields there are quite poor. In case of the reaction of this 2-chloroethanol with sulfuric acid, the symmetrical ether formed is bis beta chloroethyl ether, which again is an example of the dehydration of alcohol. As I told you earlier also, that if we want to prepare unsymmetrical ether, dehydration of alcohol is not a good method because we do not get good yield of unsymmetrical ether if we start with more than one alcohol in case of dehydration reaction. And that is why a specialized method has been utilized for the preparation of unsymmetrical ether, and that is called Williamson's ether synthesis. In this Williamson's ether synthesis, the alcohol is first treated with strong base like sodium hydride or sodium in presence of tetrahydrofuran. Formation of sodium alkoxide takes place. If we start with butanol, tertiary butanol, the product formed is sodium tertiary butoxide. This sodium tertiary butoxide is a strong base and attacks the methyl iodide, generates tertiary butyl methyl ether in very good yield. So, in other words, we can say that if we want to prepare unsymmetrical ether, Williamson's ether synthesis is a better method for the preparation. Theoretically, it has been found, or you can see that when there is preparation of an unsymmetrical ether, two pathways are possible. Like in this particular case, you can see that isopropyl methyl ether can be prepared by the reaction of sodium methoxide and isopropyl bromide. This can also be prepared by the reaction of methyl bromide and sodium isopropoxide. Now, the question arises, which of the method is feasible, which of the method is going to give us the product of our requirement. See what happens in case of path A. When we are using a strong base like sodium methoxide, instead of substitution, elimination takes place and the major product formed is propene and not the ether which actually we want to prepare. On the contrary, if you look at path B, it is methyl bromide which is attacked by the strong base, and when a strong base attacks a primary alkyl group, then there is no possibility of rearrangement or elimination, and that is why the product ether is formed in quantitative yield. Or in other words, we can say if we want to prepare an unsymmetrical ether by Williamson ether synthesis, it is always better to use the primary alkyl part as the haloalkane and the secondary or tertiary alkyl part as their sodium salt. We will now discuss the intramolecular Williamson synthesis, which results in the formation of cyclic ethers. Actually, here we utilize a class of compound called halohydrin. Halohydrin are the compounds which contains a halogen atom and a hydroxide. Like in this case, you can see that 5-bromopentanol has a hydroxy group and a bromine attached to it. Now, when this molecule is treated with a strong base like sodium hydride in tetrahydrofuran, first there is removal of proton and generation of this anion. This alkoxide attacks intramolecularly the carbon containing the bromine via this SN2 mechanism, and there is formation of this pyran molecule or oxacyclohexane molecule. The next method for the preparation of ethers is by the action of diazomethane on alcohol. It has been found that when alcohol is treated with diazomethane in presence of boron trifluoride, they form methyl ethers, because diazomethane provides CH2 group, and that is why the product formed is always a methyl ether. The function of boron trifluoride actually is to form the complex with alcohol molecule. Actually, you can see that oxygen of alcohol has lone pair of electron and boron of boron trifluoride is electron deficient. This basically is an Lewis acid and this is a Lewis base. So, this is basically a acid base reaction, formation of this protonated complex followed by removal of proton. Now, in the second step, this alkoxide RO minus attacks the electron deficient methylene group and generates the methoxyalkane, or we can in other words say that methoxy ethers are produced by the reaction of alcohol with diazomethane. Ethers are also prepared in good yield by the reaction of alkyl halide with dry silver oxide. When alkyl halides are heated with dry silver oxide, there is formation of ether in good yield. Unsymmetrical ethers may also be prepared by using two different kind of alkyl groups in alcohol and alkyl halide part. Here you can see that this is one alcohol, silver oxide and alkyl halide has been taken here. As a result, we get an unsymmetrical ether formed. This method is a good method again for the preparation of unsymmetrical ethers, and tertiary alkyl halides undergo substitution unlike elimination in the earlier case in case of Williamson ether synthesis. So, we can prepare unsymmetrical ether having tertiary alkyl group by this dry silver oxide method also. An example of silver oxide catalyst ether formation is a variation of actually the Williamson ether synthesis, in which the alcohol groups present in the molecule are methylated with the help of methyl iodide in presence of silver oxide. This is an example of alpha D glucose which has 5 hydroxy groups. When it is treated with methyl iodide in presence of silver oxide, it forms alpha D glucose pentamethyl ether. All the 5 hydroxy groups gets methylated and the product formed is in good yield, that is of about 85% yield is formed in this particular case. Ethers can also be prepared by alkoxymercuration demercuration reaction. Alkoxymercuration demercuration reaction actually is the addition of alcohol along the carbon-carbon double bond. You can see here in this molecule we have propene reacts with mercuric acetate in presence of methanol, followed by reaction with sodium borohydride, and there is formation of 2-methoxypropane. The alkoxymercuration involves addition of ROH along carbon-carbon double bond according to Markovnikov's addition rule. Now, what is Markovnikov addition rule? I think you remember we discussed it when we discuss the addition of water or addition of hydrogen halide along the carbon-carbon double bond, and according to this rule the positive part of the addition product goes to the carbon atom having more number of hydrogens, and here H, that is why, goes to this end terminal carbon, and resulting product is an ether. The mechanism of alkoxymercuration in case of alkenes. If you remember, if we undergo reaction of alkene in presence with mercuric acetate in presence of water, then the product formed is an alcohol. Here this is a carbon-carbon double bond. First there is mercurinium ion is formed, followed by the attack of the weak nucleophile water, followed by the reaction with sodium or borohydride to form this alcohol. Now we will discuss the reaction of methanol on 1-methyl cyclopentene. 1-methyl cyclopentene is an unsymmetrical alkene. The first step is the formation of bridged mercurinium ion along the carbon-carbon double bond, and the second step then is the attack of methoxide, the nucleophile. Now methoxide can attack this carbon as well as this carbon, and then formation of the product can take place, but methoxide attacks preferentially the carbon which forms a more stable carbocation, and more stable carbocation is generated at a position which is more substituted, and that is why the methoxide attacks this carbon, followed by the reaction with sodium borohydride. The product formed is 1-methyl 1-methoxy cyclopentane. Once again summarize what actually we have done throughout this episode. In the beginning we introduced what actually are ethers. We introduced that ethers are derivatives of alcohols. They are the derivatives of water also, we can call them, because replacement of hydrogen by alkyl generates ethers. We discussed in today's lecture the structure of ethers, we discussed the classification associated with ethers, we discussed in detail the nomenclature of different types of ethers, then we discussed the isomerism shown by ethers. The two isomerisms shown by ethers are functional isomerism with the alcohol molecule and metamerism shown within ether molecules. Then we discussed various methods of preparation of ethers starting from alcohol or alkyl halide or alkenes. Starting from alcohol, we can prepare ethers via dehydration reaction. In case of Williamson ether synthesis, we utilized alcohol, converted alcohol into their sodium salt and alkyl halide. In the reaction with diazomethane or silver oxide, we utilize alcohol and alkyl halide. Lastly, we can prepare ethers by starting from alkenes by the reaction with alcohols, and the method is called alkoxymercuration demercuration reaction. So, with this we have discussed all methods for the preparation of ethers. In the next lecture, we will discuss the physical and chemical properties shown by ethers. Thank you very much.